Sometimes an infinite space via 3 that varies we have a space your diameter is going to be positive y direction. Time dependent. And here, and you have time. The root is a different d and the y. You're also given the dependence of your curve. So from zero, T1 returns as linear and once it's also constant from T1 to T2, and then the decreases linear. So this is minus this linear value here. This right here. So in the first part, they're asking you about flux through the loop at point of time t1. And you're given the values angle, like I1, and I4, I'm not giving the values for the value. I'm also given L, and so out of line you don't know. You don't know. There is so in the first part you have to find flux through the loop at time t equals. So how would you think you should think you did something similar to this in the
Right.
What is plug different? Similar to electric field, right? So you have the integral of B, what, dA. So in this case, you have your in this case the loop is not moving anymore. However, you will have induced EMF later in the problem because you have a type 10 dependent, correct? So the flux through the loop is going to change not because the loop is moving, but because the current is affected. It will produce different magnetic fields. Okay. So in this case, what's the direction of the field in the area of the loop? Due to this wire. You use the right hand rule, right? So thumb is pointing the direction of the current, fingers around. So at this location, you have field into the center. It will be denser closer to the wire, and it will be less dense. And it will be more dense. So what's the formula for the B field? So the magnetic field created by an infinitely long straight wire. It will be mu naught times I of T1 over 2 pi r, right? Where r is the distance from the wire. And dA is given by W times dr. Right? Where r is the distance from the wire. So what are our limits of integration? We are integrating over going along the x-axis. So that's why I picked so that's why dA is given by W dot dl. So we're integrating over the area.
So
Remember, we need r.
Yes.
So
from
yes.
so equal.
Yes. That's it. So in this integral, what is constant that you can pull out of each? Everything except for R. Well, we have time dependent current, but we need to find flux at some certain moment. So at some certain moment, we have some certain current, right? That's not changing. We're changing the air, the VO. So we can put I of T1 out of the so T0 times I of T1 times W over T I. And so for the integral, we just have from B is equal to L of PR over. So what's the value of B? Do you know?
Yes.
Yeah, and you can pull it into one integral.
Both.
So that's your flux at time. In the second part, you're doing the first part. So for the second part, they're asking for induced EMF at time equals at some point of time. Well, it's given. The time is given, and for me, that time was between 0 and 1. So it's on this rising slope. I believe for you it's right? So let's call this time tau 1. So they're looking for the induced EMF at time equals tau 1. Or tau 1 is given. I'll say tau 1 of something. Right. So, what do you think it's doing? You should remember that induced EMF is given by the formula of this fluid. Is given as, okay, not for this loop. In general, it's EF DC, right? Minus. Okay. And in the case of the loop, it was in the box that I provided, that is given by delta C, delta F, or delta C. What's delta F? Delta F is mu naught times natural log of d plus L over L, sorry, over d times delta t delta. Actually, alternatively, let's do it with let's do it with this. So this is equal to minus d dt. Oh, we just found the field. Well, sorry, we just found the flux. So this is d naught d delta over 2pi and natural log of d plus L over d times pi. But I is this itself. All of this pretty much is constant, so we can pull it out of the differential, right? This is equal to negative mu naught times delta over 2pi times natural log of d plus L over d times the I. The only thing that's changing in time in this case is the current. So the IDT is just at point 1, is the slope of the plane, which we can easily find, right? Because we start at the origin and then we come to a certain point right here and have I1 and T1. So the IDT in this case is simply I1 over T. So delta I will be delta. Okay? The slope, just correct it like that. Just imagine that you have a line coming through the origin. You know this coordinates right here and those coordinates right there. So you can find the slope and you can find the whole equation. So in this case, as we continue, it's going to be minus mu naught times W over 2pi times natural log of d plus L over d times I1 over yes, it was different. Well, I'm just saying that they're asking for the induced EMF at time one. Sorry, at time equals L1. I'm not sure. I mean, I asked Harry that his L1 was between 0 and 1. So I just picked this as L1 and said my current is going to be something here. So that's the bottom down here is the formula for your EMF. Now let's double check the EMF can be either positive or negative. So let's double check the sign EMF that's in there. So in this case, the current through the wire is increasing, right? So the field and the flux through the loop is increasing. So in order to keep the conservation of energy holding, you need the induced EMF to oppose the increase induced current, so that field that is applied in the pole stays with the flux, so that the field induced is opposite to the one created by that. Okay? Okay, think about it this way. The current increases, so the B field becomes stronger, and so we have more flux in the loop. The loop is stubborn. The loop doesn't want any more flux, right? So it will make its best, do its best not to, so that the flux fluid doesn't increase at all. So it will create such current that would oppose. So it would create a current that would create a field that would oppose the one that we have right now, because the loop, yeah, it's the current, right? There is a induced current in the loop, and this current creates the field. The field would oppose to the field that's given by the loop, by the straight current. So just remember that the loop is always against everything. You increase the field, it does no. You decrease the field, it does no. Thank you. So okay, let's continue our discussion. So in this case, current through the wire increase means the B field increase, means the flux increase. We want the opposing field. So if our field is into the cord, we want the current in the loop to create the field out of the cord. So our current will go in the counterclockwise direction. And according to the problem, if current is counterclockwise, then E must be further here. So this formula right here should give you the method. That makes sense? Okay, good. We can put it. Okay. You can go to the third one. I'm sorry, I have to that's the first. In part B, like we are asking for we have to look at the list and find some other problem. It's hard without numbers. Let me give you my number so that we can see what's going on. For me, T1 is equal to 13 seconds. T3 is 20.5 seconds. T4 is 23 seconds. And so in this part, they're asking me to find EMF. I find how to go to 15 seconds. We already found one EMF, but at that time we were sure where our power was. Remember, in this case, we could easily see from the values that tau 1 is between 0 and T1. For this case, you can see that my tau 2 falls between T1 and T3. So this is my T1. Sorry, this is my T3 and this is T1. So I have two options. Option 1, my time tau 2 can be between T1 and T2. But at that time, I have constant current, which would not give me any change of flux. It would not induce any EMF. So that's an easy. Or, alternatively, my tau 2 can be between T2 and T3, in which case I will have induced because I have change of current, change of flux. So what we need is we need to find T2 and define which one of the two options is correct. So what are your suggestions for this? This is mostly enough. How do you suggest we find T2? You know the coordinates of T3 and T4. So we can find the equation of the line and see where it crosses. I should also give you my eyebrow. So my eyebrow is it okay? Is it like so what I do is I'm using, you know that this is, I'm using this equation for the line. Y equals AX plus B. Okay. So for this point, we have Y, which is in this case Y, and U. 0 equal to T3 K plus B. At this point before, we have and 4 equals to not to solve this with that in my case, when I substitute my 1, I'll get negative 0.8 on my slope. And I also can find b from one of these equations, and for me it was 16. So the equation of this line here is I equals minus 0.8 t plus 16. So now we need to find the curve that this keep together. Okay? And we know that at T2, our current is I1, which is given up. So I1 equal to minus 0.8 T2 plus 16.4. Therefore, I1 minus 16.4 over minus 0.8. In my case, T2 was 18 seconds. Okay? So this right here is 18 seconds. They are asking how the induced EMF at tau equals 15 seconds. So at which of the intervals does my tau come? At the constant interval or at the slope? At the constant. Keep tau constant. From here you can see that EMF given by minus df over dt that's given by minus naught times w over 2 times natural log of t plus f over d times the I to t equal to because the slope of the item. Indeed, our slope isn't moving, our curve doesn't change, so the loop is moving, nothing is changing. The loop doesn't have to change, nothing is changing, the loop is moving, nothing has to change. In part 4, we are asking you we're asking you what the direction of the curve in the loop. And how? And I'll read it. Cell 3 is 2.5 seconds. So at cell 3, about 25 seconds, we're on this graph. 53 is, oh yeah, this is at 53. Exactly at 53. So what's happening in the direction of the use What do you mean by current is going down? So are we going in the negative y direction? In fact, the current is zero. What? EMF and hence current, we need to change of flux and the change of I, and the I itself. We don't care about I. As long as it's changed. What are you bypassing? What's the direction of the induced field? That way it would be even. Like however much field and flux you have will be even multiplied by that also that current. Ooh, it's doing its best to keep everything constant. Isn't it right? Oh, the conservative. The conservative. So in this case, the direction. The loop would try to keep it as an open. Well, yeah, the current in fact goes negative, so it means that current changes direction. But I'll take it. You're asked about just. So originally, yeah, let's think from the increasing focus. Sorry, from positive. So let's say the current has just been passed. So my field is decreasing and is decreasing from the direction input. So the loop will try to induce such a current so that its field is into the board, trying to keep everything as it used to. Right? So that to keep the flux through it into the board. So if the flow is induced field into the board, that means you have yes. So let's think from this perspective. You should have current in the clockwise direction. Okay? Let's now think about this. Your friend has just done that. Just about. So your current is about to flow that direction. Right? So your field is about to be pointing towards it, right? And it will just after it will get lifted. So it will flow down. It will induce the field just into out of the door towards you, right? And it will roll. Who doesn't want who doesn't want it to roll? It will try to oppose it and place its field against this increasing current towards it. So it induces field still and your current will go. And it decreases because that will decrease. I mean, we're on the same slope, right? So current is going down, it shouldn't be going through. It shouldn't be going. Yes, the field index, the field due to current index will try to prevent the increase. So once you're decreasing the positive current, it will try to keep it. Once the current goes negative and starts increasing it, so it will try to decrease its increase as much as possible. So it will be pointing in that direction. This current flips its field like this to this. But the loop is still being there. So think about it this way. Remember the pendulum like this? Remember? No, professor. Okay, let's call the original direction of the into the plane being constant. Let's say constant. Okay? So your B field induced by the change in current and the decrease in 2, 0 and an output field would mean that the field would decrease, and go to something depth to negative. And the loop wants to keep it as it used to be up. Maybe think about it as a loop, as an old blade. The old blade is like things as they were when she was young, right? So the loop liked when the field was changing and what was positive, right? And so then the field, even though it's negative, the loop would still try its best to make it positive. The loop would very much increase, so even if it's negative, it's still works. That's that. And I know first part. Your opinion? Will induce EMF at time call electrical Michael 4 is only else. So in this problem, you really have to pay attention to on the graph of curve. So let's see. Tau 4 is between T3 and T4. Right? According to so let's Tau 4 is 21 seconds. Let's see if this is so it's similar to our original one, your email. Minus B block and natural log of plus the and minus this B R. It's very much similar in second person. So we know you're not obvious W to by everything. We want to look at this time. I mean, you can talk to it. Don't forget that this slope, according to our previous calculation, with my value, was negative 0.48. So this negative times that one should be according to EMF. Let's think whether it's right. So now my current is going in the negative. And as we determine our induced field, it's going to be induced. Right? So my current is clockwise. Right? According to book law, according to the wording of the law, if the current is clockwise, that means EMF is greater than 0, which is just what we got because we have negative 0.8 times this negative. So our EMF is greater than 0. Okay. Let me see. I haven't looked at that. Which of the following statements about the magnitude of the flux through the loop? In my case, it's 1/4 of a period. And I'm not. Mine is like a third. Right? So in my case, the period is 1 second, and you're asking about the flux and the current at 1/4 of the period. What is meant by M2? This number. So at 1/4 of the period, let's say and D is pointing out like this. So at time which is equal to 1/4 of the period, where would your loop triangle be calculated? It will be pointing like this there. It is like this and it looks like. So they're asking about the induced current of flux. So flux is given by integral of d dot dA. Remember that dA refers to the normal to the surface. So in this case, normal is along d, right? The normal is along d. So your flux at this point is not okay, which is given to integral of d times a times cosine theta, where theta is the angle. Right? So flux is maximum when this term is 1. So cosine is 1, or I mean 0 or 180, but in that case they would point in the opposite direction. So in this case, dA is pointing perpendicular to the surface along, right? So the cosine, so the angle between them 0. So flux in this is not current is given by EMF over R. EMF is minus P of PT over R.
Is this when
It's asking at one foot, so when the okay, let's now think about the flux when it's neutral takes place. So now your load is in this position, 140. So your dA is perpendicular to the v field, right? So you don't, so cosine between 0, so you have to plug 0. Also think about it.
how though? Because the video is pointing out like this. So then you're, let's say it's in a triangle, right?
This is your triangle, right? When it's right.
Right. So then your area is pointing out like this. So then the video is pointing out like this. Your area is pointing out like this. That means that 90 degrees.
Yeah, sorry, the angle between the side, I just jumped and said like this.
Oh, okay.
The angle is 90. Cosine 90.
So
I'm sorry. So, also, you may think about it as, yeah, your B is like, your field is piercing the space, right? So when you turn your loop like this, it's piercing everywhere, right? Or when you turn your loop like this, perpendicular, well, not perpendicular, like this, 1/4 of the field, you minimize the area that the flux can keep. The flux cannot keep anything there, assuming that the loop is, it cannot keep it. So you're basically hiding this whole area from the field. That's why the flux field. You're not allowing anything to take place. So when you move it like this, flux is there. Now let's think about I. I is given by induced EMF over R, and EMF is given by negative rate of change of flux in R. Okay. In this case, it can be also written as, I think they give you this formula in the pivot table, that dF dt, which is equal to EMF, also is given by the formula of E times A times omega times cosine of omega. This all over. No, in this case, you're correct. Right. No, this is a different also. See, in this one, theta is the angle between B and dA. In this case, you have omega t. No, I forgot the pi over here. Let's think. Let's think about it this way. And if this is your original position, dA is that way, B is that way. So the angle, yeah, the angle between theta is here. I'll think about it.
Can you send it? And also, can you send it to Justice?